Hello dear students and welcome back to this session of mechanical system design. We will be discussing today on machine tool gearboxes. In previous video we have covered introduction part of machine tool gearboxes. In this video we will cover various types of gearing laws used in a design of machine tool gearbox. Then various structural formulas, how to draw speed diagram, how to draw array diagram, and how to predict which one is optimum. In this video we will cover all these things. Myself, Professor M.R. Pardeshi from Mechanical Engineering Department from Kekewag Institute of Engineering Education and Research, Nasik. So welcome students. So various laws of step regulation. There are 4 laws of step regulation in machine tool gearbox design. So first law is a arithmetic progression, that is the RPM constitutes arithmetic progression. Then geometric progression, third one is harmonic progression, and fourth one is logarithmic progression. So we'll see one by one and which one is feasible while designing of machine tool gearbox. We will see that. So first one is arithmetic progression. In arithmetic progression, the difference between any two successive spindle speeds is constant. Means suppose if you take any two spindle speeds, or it will be a successive, so that is constant in arithmetic progression. So it is indicated by A. So A is equals to n max minus n minimum upon z minus 1. So the successive spindle speeds, or the difference between the two successive spindle speeds, are constant. So as per our definition, we will write here n max minus n minimum upon z minus 1. So n1 is our n minimum, and let's say n max is the maximum speed. So from this we will calculate the which type of diameter that can be turned on that machine tool, that is dx. From the pitch line velocity we have calculated, that is v is equals to pi dn upon 1000. So dx is nothing but dx is equals to 1000 v upon pi into nx. And lower limit of diameter, that is obviously dx plus 1, that is 1000 v upon n x plus 1 into pi. So diameter range, that is delta dx, that is again difference between the lower diameter and the major diameter. So dx minus dx plus 1, that will be the diameter range or difference in the diameter range. So delta dx that can be calculated while putting the values of dx and dx plus 1, we will get 1000 v upon pi into 1 upon nx minus 1 upon nx plus 1. So from this we will take one example. So the example is maximum spindle speed is 375 rpm and minimum spindle speed is 30 rpm. The number of speed steps we will take, for example, is z is equals to 12, and cutting speed we have taken as v is equals to 20 meters per minute. So as we have calculated arithmetic progression, that is A, so n max minus n minimum upon z minus 1. So we know that n max, we know n minimum, we know z. So while putting the values we will calculate A. So and phi is nothing but the ratio of two successive spindle speeds. So dx again calculated and delta d also we can calculate. So we prepare one table while calculating nx, phi, dx and delta dx. So all the values, corresponding values, we are calculating for n1 to n12 because z is equals to 12. So there are 12 number of spindle speeds are there. So and we prepare one table while putting the values and calculating dx and delta dx. So if you see the first value, that is n1, that is 30 rpm, and phi is 2.04 and dx is 212 and delta dx is 108.3. So simply if you see at lower spindle speed range, that is 30, 61 and 92.8, so you'll find here very wider range of delta dx. So see here 17.3, directly 35.1, and directly 108.3. And if you see the higher spindle speed steps, that is 312, 344, 375, very wider or very narrow range of delta dx, isn't it? So 2, 1.9, that is again 2, and 1.6. So it is very narrow, or we can say it is redundant, isn't it? So at higher spindle speed steps, the delta dx is very narrow, and at lower spindle speed steps, the delta dx very wider. So it is conclusion from this particular table. Again, we'll see the another type of speed regulation. See here, at lower speed and at higher speed. Then the another type of step law, that is geometric progression, that is GP. The ratio of two successive spindle speeds steps are constant. Now in previous case what happened? It is the difference between the two successive spindle speeds. Now the ratio of two successive spindle speeds are constant. Means what? The ratio, that is the significant successive spindle speeds, we take the ratio. So geometric progression ratio, that is phi, is constant. So phi is the ratio of two successive spindle speeds. So n1 to nz. N1 is obviously it is the lower spindle speed, and nz is the maximum spindle speed, isn't it, or last spindle speed. So given, suppose again z is the number of spindle speeds, n minimum is the minimum spindle speed, and n maximum is the maximum spindle speed. So phi is nothing but, as I told you, or the definition says, the successive spindle speeds are constant. So again, phi is equals to n2 by n1 is equals to n3 by n2 up to nz by nz minus 1. So successive spindle speeds are constant in the geometric progression. So again, we'll take the range ratio. What is meant by range ratio? So range ratio is indicating by Rn. Again, it is n max upon n minimum. So n minimum is equals to n1 and n maximum is equals to nz. So Rn is nothing but, so nz upon n1 is equals to nz upon n minus 1 up to n3 by n2 into n2 by n1. So Rn is nothing but phi into phi up to phi into phi. Okay. So Rn is equals to phi raised to z minus 1. So again, take the log on the both side and we'll get the phi is equals to Rn raised to 1 upon z minus 1, or we can say that z is equals to log of Rn into phi upon log of phi. So we can easily find out the z and phi and Rn. Then we'll take example for solving this particular geometric step law. Maximum spindle speed we have taken it as a 375 rpm, and minimum spindle speed we have taken at is 30 rpm. The number of speed steps it is involved, it is again z is equals to 12, and cutting speed we have taken is again 20 minutes per minute. So phi, as we have discussed in the earlier slide, phi is equals to Rn raised to 1 upon z minus 1. That is by putting the values, and we'll get 1.26 is the phi. So by putting the values of phi, we'll get the corresponding values of n1, n2, n3, and likewise up to n12, because we have taken the number of speed steps z is equals to 12. So accordingly, again we will get the dx and delta d. Okay, and again we prepared one table, as we have prepared a table in the case of arithmetic progression. Again, same table we are preparing for nx, for phi, here is dx and delta dx. So again, we can say that from this particular table we conclude that at lower spindle speed steps, isn't it, means what, suppose n1 is equals to 30, what is the value of phi? 1.26, and what is the value of dx? 212, and delta dx is 42. So here we observe that at lower spindle speed, the delta dx is comparatively not wider as compared to arithmetic progression. Still it is wider, but it is not wider than that of the previous case, that is arithmetic progression. And at lower spindle at higher spindle speed steps, or we can say at higher spindle speeds, the delta dx or the diameter range is redundant, or we can say it is comparatively same. means 6.5, 5.8, again it is 6, and 4.2, again it is 4. So we can say that at a higher spindle speed steps, the delta dx is narrow, or we can say that it is redundant. So comparatively, as compared to arithmetic progression, in geometric progression at lower spindle speed steps, the delta dx we have calculated, it is a not wider as in case of arithmetic progression, isn't it? So in harmonic progression, again the third case, in harmonic progression, what is the definition? The diameter range saved by each rpm of progression is equal. The diameter range served by each rpm of progression is equal. Means what? Again another definition is, if you see that the reciprocal of the successive spindle speeds is constant. Difference between the reciprocal of successive spindle speeds are constant in case of harmonic progression. So again the another definition is, diameter range served by each rpm of progression is equal to, or is equal. That is, diameter range delta dx is equals to dx minus dx plus 1, that is constant. So here, so again, so as I told you, the reciprocal of and the difference is constant. So the diameter range, reciprocal and the difference is constant in case of harmonic progression. So again, let us take one example, another example, and we'll solve that phi dx and delta dx. Again we'll prepare one table for this particular values for n1 is equals to 30 up to n12 is equals to 375. So again we'll conclude that from this table, at higher spindle speed steps, suppose the higher range, we are considering the 3 spindle speed steps at higher range, and we conclude that here delta dx is 18, 18 and 18. So it is redundant again. So we cannot use that particular progression or harmonic progression law while designing a multi-speed gearbox or machine tool gearbox. So in case of that, again one drawback is that higher spindle speed steps, there is no means what, the redundant delta dx we got, and obviously at lower spindle speed step also we got the same results. So it is not being used generally. So we are only to compare in arithmetic progression and geometric progression, we need to solve that. So we'll see that why the geometric progression is going to take while designing a machine tool gearbox. So first advantage of geometric progression is, first is constant loss of economic cutting speed. So in that case, what happened? The difference between the actual cutting speed and optimum cutting speed is known as the loss of economic cutting speed. So what happened? We draw a graph from the cutting speed available on the y-axis, and on the x-axis the workpiece diameter is there. So you can easily say that, so nk is our actual speed. Let's say nk is our actual speed. So difference between the actual speed nk and n optimum, that is the constant loss of economic cutting speed. And again nk plus 1, that is again our actual cutting speed in case of machine tool. So the difference between nk plus 1 and n optimum, again we got a constant loss of economic cutting speed. And significantly, the constant loss of economic cutting speed we got in geometric progression, because in that geometric progression we have seen that the definition that the difference between the ratio of two successive spindle speeds are constant, and we get phi is constant. So the ratio of two successive spindle speed is constant. So ultimately we can have the constant loss of economic cutting speed, because actual cutting speed and optimum cutting speed difference we got constant. So that's why the constant loss of economic cutting speed we got. So here again we putting the values. So v is equals to pi dn upon 1000, and by putting the values n1 to n plus 1, and in between that n optimum is there. So our actual speed, that might be n1, or our actual speed, that might be n plus 1, isn't it? So here the difference between these two speeds with optimal spindle speeds, that is called economic cutting speed. So we got economic cutting speed is constant in geometric progression only. So again we can say that This will be the one of the advantage. So we can say that V optimum we can solve it at pi d upon 1000 into nk plus nk plus 1 divided by 2. Okay, so by solving this we come to know that Vmax means cutting speed maximum cutting speed is totally depend on phi. So Vmax, it is the maximum cutting speed, is equals to phi minus 1 upon phi plus 1 into V optimum. So in what geometry or in what progression ratio we got the phi constant? So obviously the answer is geometric progression. So that's why the cutting speed, maximum cutting speed is there, it depend on the phi, and in the only geometric progression we got phi is constant. So once the phi is constant, so we got cutting speed is constant. So Vmax is equals to phi minus 1 upon phi plus 1 into V optimum. From this equation we can conclude that the constant loss of economic cutting speed is getting in only in a geometric progression. Then another advantage of geometric progression is better design feature. So in case of geometric progression, the design feature is we got the better as compared to another progression law. Then the standard values of geometric progression, that is phi. So what are different standard values of phi? From it is ranges from 540 to 510 about 10 by 3. So and it is based on the preferred series. So R is equals to 40 under root of 10, that is 1.06 to 2. So that phi value of phi is varying from 1 to 2, isn't it? So phi is equals to, it is depend on range ratio, phi is equals to Rn raised to 1 upon z minus 1, and it is depend on the various application also. So machine tool, so the lathe machine, it is range ratio is 40 to 60, milling machine 30 to 50, shaping machine is 10, drilling machine is 20 to 30, and grinding machine is 1 to 10. So depending on various types of machine tool, recommended values of phi is given, or the preferred series or standard values of geometric progression phi is given. But remember, from the standard values, phi is only varying from 1 to 2, because if it is nearer to 2, then what happen? We are saying that very small speed changes is there, or we can say that your gearbox is very complicated because it is the phi is very nearer to 1, and if it is nearer to 2 or it is up to 2, so the speed steps, spindle speed steps we got, it is wider. So depending on application, depending on the finishing product we required, and different speed is required for finishing operations, so we have to select the phi accordingly. So it is, if it is nearer to 1, so we can get the very narrow spindle speed steps, and if it is nearer to 2, we can get the wider spindle speed steps. So we can say that at which application is suitable, and we can select a phi accordingly. So these are the standard values of geometric progression. And the next topic is how to draw a kinematic diagram of a gearbox. So after knowing the various speeds while taking a phi is constant, we got the speed from n1 to nz, or n minimum to n maximum. So the kinematic diagram gives you the, or it gives the decide the number of shafts, then it decides the number of gears involves, and how much gears involves on each shaft, then decide the arrangement of gears on each shaft, and the calculation of number of teeth. So all the information we can get from the kinematic diagram. So then we will see the structural formula, how to draw a structural formula, how to draw a structural diagram, and how to draw a ray diagram and speed chart. So we'll see in one by one. So first is the formula, structural formula for Z is equals to 3. So as in previous video, as I told you, so Z is equals to 6. So 6 is to be split up into 2 or 3. So here Z is split up in 2 or 3. So 3 2s are 6. So we got the values of P1 and P2. Here is P1 is 3, P2 is 2. So P1 is 3, P2 is 2, and we got the multiplication in two factors. So we got n is equals to 2. So capital N is nothing but the stages involved in the gearbox, that is 2. So maximum structural formula, what are the number? So n factorial square, that will be the maximum structural formula, or we can create the combination of that particular structural formula, that is n factorial square. So here is n is 2, so 2 into 1 2, 2 square is 4, so 4 maximum structural formula can be drawn. So how it is to be? So here is the total p combination is equals to 2 and total x combination is equals to 2. So by changing the position of p1 and p2 and changing the position of x1 and x2, we got the structural formula like this. So z is equals to 3 into x1, 2 into x2. Then second structural formula, by putting the value of p2, that is 2 into x1, 3 into x2, and another is the changing the values of x1 and x2. So now the 3 into x2, 2 into x1, and 2 into x2 into 3 into x1. So this is the structural formula we got, that is 4 different structural formula we got from z is equals to 6. So here x1 is equals to 1 and x2 is equals to p1. So here we put the values, z is equals to 3 of 1, 2 of 3, z is equals to 2 of 1, 3 of 2, and z is equals to 3 of 2, 2 of 1, and z is equals to 2 of 3 and 3 of 1 by putting the values of x1 and x2, p1 and p2 in the neighbor equation. So we got this, and now we have to predict what is meant by structural diagram. So structural diagram or the structural formula is going to represent a spatial graph called structural diagram, or you can say that it is differing from the German layout. So it is, first of all, we need to draw a z number of horizontal lines. So here z is equals to 6, so horizontal lines are 6. So total speed steps it is indicating, suppose z is equals to 6, so n1 to n6 horizontal lines we have to draw. Then second step is to draw n plus 1 number of vertical lines. So here n is equals to 2 because we are splitting the z in 2 into 3. So 2 into 3 will be the number of stages involved, that is n. So n plus 1 vertical lines we need to draw, that is total shaft it is indicating. Then third step is the distance between the two horizontal lines is log phi, obviously, because we are following the geometric progression, that is phi is constant, or the ratio of two successive spindle speeds are constant. So log phi is constant, so the distance between the two horizontal lines is constant. So distance between two horizontal lines are log phi, that is phi. So using structural formula, draw structural diagram. So from any one of the structural formula we have seen in earlier slide, so we need to draw structural diagram. So structural formula for z is equals to 6. So these are the structural formula we got in previous slide, again I repeat, and we need to draw a structural diagram. So as I told you, or in previous slide, there are 6 number of horizontal lines. So we count that n1, n2, n3, n4, n5, n6. So 6 horizontal lines are involved and 3 vertical lines are involved, 1, 2 and 3. So n plus 1 vertical lines. So n is 2 here. So 2 plus 1, 3 vertical lines are there. And as we have seen, the distance between the two horizontal lines are log phi because the phi is constant. We are following the geometry progression. Okay, so here this is the first stage. So first shaft 1 to shaft 2, this is first stage. Then shaft 2 to 3, this is second stage, and or we can say second shaft, and the third vertical line indicating the third shaft. Okay, and if you talk about the stages, so this is first stage and this is the second stage. So likewise we need to draw a structural diagram. So here we are giving the number n1 to n6. Okay, here structural formula 3 of 1, 2 of 3 we write because z is equals to 3 of 1, 2 of 3, and we have find out the middle portion. Okay, so first 2.5 and from the upper one 2.5. So this is the middle portion. Okay, and we draw a horizontal line or green line. If you indicate, green line is there, it is the middle portion of this structural diagram. Then third step, what is the third step? Here, what is the structural formula? This is 3 of 1. The meaning of 3 of 1 is 3 rays are created in a gap of 1. Okay, in a gap of 1. 3 rays are there in a gap of 1. One ray is constant, means we got constant speed at this line, we got increasing speed, and we got decreasing speed. So remember that, but if the gap of these two lines is 1, because here x value of x is 1 and value of p is 3. So p is indicating the how much speed is increasing, constant or decreasing, and x is indicating what is the difference between the two successive spindle speeds. So here difference is 1. So easily understood. So here half portion is there and half and half 1. Here is also half and half and half 1. So one line is there, 1, 2 and 3. So 3 lines are there in a gap of 1. So 3 of 1. So this is the first stage. Then second, what is the structural formula? Here 2 of 3. Now 2 lines are there. Okay, the value of p is 2. Okay, it is indicating by blue line, and the difference between these spindle speeds are 3. So now here the 3 spindle speeds we got. So in a gap of 3. So here 2 is there. It is indicating by p, and 3 is there. So in the gap of 3, you see this is 1, 2 and 3. So the lines are 2. Here is 1 and 2. In previous case what happened? One speed is constant, one is increasing, one is decreasing, but here only 2 speeds are there. P2 value is 2 only. So there are 2 speeds only, and but here the gap of between the 2 speeds is 3, because the 3 lines we need to cross. Okay, so this is the diagram. So accordingly that we need to draw for point 1, point 2 and point 3. Okay, so this is for point 2. So because in first speed we got the 3 points, 1, 2 and 3. Because in previous case we got 1 point, it is middle portion, we got the 3 points. Again we expand these 3 points. Okay, so this is second point and this is the third point. So this complete structure diagram we got. This is, and one significant amount is there. So at the end of all the rays are completing. So if you find here blue lines, it is completing all the diagram. So N6 to N1. Okay, so it is full. So here if one of the ray is missing, so you get the indication that your structural formula or structural diagram is something getting wrong. So now we will draw a for z is equals to 12. So z is equals to, again z is splitting it into 2 into 3. So here I am splitting up z is in 3 into 2 into 2. So it is indicating P1, P2 and P3. So P1 is 3, P2 is 2 and P3 is 2. So here now indicating n, how much n is there? So here P1 3, P2 is 2, P3 is 2. Here n is 3 because there are 3 factors are creating from z is equals to 12. So n is equals to 3. Again maximum structural formula, that is n factorial square. So n is 3, 3 into 2 6, 6 square is 36. So 36 structural formula we got from this particular z is equals to 12. So here 36 formula. So 6 times p has to be changed and 6 times x has to be changed. So there are the formula has to be permutation and combination. So the total combination is n factorial upon q factorial, that is 6 by 2, that is 3. So 3 basic structural formula we got, or the correct formula we got. So we'll see one by one. So the combination of p and combination of x we need to say. So the optimum structural formula we got from the value of x1, x2 and x3. So x1 is less than x2 is less than x3. If in that structural formula is there, those structural formula we take into consideration. That again this is the one of the method to choose a optimum structural formula from the given structural formula. Here the x1 is less than x2 is less than x3. If like this serial is there, you can say that this is the optimal structure formula. So one by one we'll see that here x1 is 1, x2 is p1, and x3 is p1 into p2. So increasing order, x1 is should be a increasing order, then only we can say that it is the optimum structural formula. So here you can say that here z is equals to 3 of 1, 2 of 3, 2 of 6, and z is equals to 2 of 1, 3 of 2, and 2 of 6. Again z is equals to 2 of 1, 2 of 2, and 3 of 4. So again you will find what is the value of x1 here, 1, x2 3, x3 6. So x is continuously increasing. In second case also x is increasing, in third case also x is increasing. So we can say that it is the optimum structural formula. So we, with the help of this, we can draw the speed gearbox, or the, we can say that the structural diagram we can draw. So again, as I told you, so the z is equals to 12, n is equals to 3. So horizontal lines are 12 and vertical line is n plus 1, that is 4. So 4 vertical lines we draw. Okay, 1, 2, 3 and 4, and number of horizontal lines are 12. So from 1 to 12. Okay, again we find out the middle portion. So okay, so here is the middle portion, 6.5 from the above and 7.5 from the below. So we got the middle portion, and from this we draw a structural diagram. So for the structural formula, first structural formula, that is 2 of 1, 3 of 2 and 2 of 6. So 2 of 1 means 2 rays are there in a gap of 1. So red line, 2 rays are there in a gap of 1. So in between that only one speed step, or the gap is 1. So 2 points are creating. Again first and second is 3 of 2. Now 3 rays are there in a gap of 2. So one is this, 1, 2. One is this, 1, 2. Okay, and again for the second point, so in a gap of 2, again the middle portion is constant speed is there. One is increasing, one is decreasing. The gap is ultimately 2, and it is again indicating the, or creating 1, 2, 3, 4, 5, 6. 6 points are creating. Okay, again the third is 2 of 6. So 2 rays are there in a gap of 6. So count this, 1, 2, 3, 4, 5 and 6. So 2 rays are indicating in a gap of 6. So accordingly all the points are covered, and as I told you, if it is completing up to this, the structural diagram is correct. So accordingly, second structural formula, 3 of 1, 2 of 3, 2 of 6, 2 of 1, 2 of 2 and 3 of 4. So all the structural formula we got and structural diagram we are made, and from this we can say that which one is suitable. Now all the structural diagram is same, all the structural formula is same, and we are applying the method of optimum structural formula, that is x1 is less than x2 is less than x3. But here is the node optimization method is there. So at first shaft here it is, what is the value of node? It is 6.5. At the second shaft, what is the value of node, maximum value of node? That is 7, isn't it? Here that is 9. Okay, here is the 9 maximum value, then it is 12. So all the addition is 6.5 plus 7 plus 9 plus 12, that is 34.5 we got. In second diagram we got here again 6.5, here is again 7.5. Okay, here 7.5, here 9 and here 12. Addition is 35. And in the third again 6.5, here is 7, here is 8 and another is 12. So addition is 33.5. So which one is lesser value of node optimization? It is 33.5. So among 3 diagram, or among 3 structural diagram, we can say that which diagram having lesser node values. So here is 33.5 we got. So this one will be our perfect or the optimum structural diagram we can use for designing of multi-speed gearbox, okay, or machine tool gearbox. So 33.5 is the lesser than that of the previous 2 cases. So we can select this diagram to for the further analysis. Then The transmission restriction for any machine tool gearbox, that should be I max into I minimum, that is 1. Okay, so here one input yields two speeds on the next shaft, that is N1 and N2. So here is the N1 we got and here N2 we got. So this is the input speed, here is the cluster is using. Okay, and here P, value of P is 2. So basically the maximum increase of the speed in the transmission gearbox and the minimum or the reduction of the speed in the transmission gearbox, that is 0.25, and the increasing speed, that is double. So transmission range for this particular transmission gearbox is to ensure the radial distance is not larger. So here, so the, as I told you, the maximum increase of the speed, that is twice, or it may be double, or minimum reduction, that is 0.25, or that's why the transmission range, that is 8. So I max upon I minimum, that should be 8 only, to avoid the radial distance is not larger, because in case of machine tool gearboxes, very less space is provided in machine tool. So we have to take into consideration that the transmission restriction also. So keep in mind the maximum increase of speed in transmission gearbox is doubled, or minimum should be 0.25 or 1/4, isn't it? So ultimately we got N max upon N minimum is equals to 8. So that's it from this today's lecture. So thank you for watching. In next lecture we will see how to draw the ray diagram and speed diagram in detail. Thank you all. Thank you.